Today we are solving task scheduler problem. This problem statement is kind of dense, so I will try to note down some of the key points in the problem statement. Given a character array tasks representing the tasks a CPU needs to do, where each letter represents a different task. Tasks could be done in any order. Each task is done in 1 unit of time, and for each unit of time, CPU could complete either one task or just be idle. However, there is a non-negative integer n. Non-negative means it's either greater than or equal to 0. Non-negative integer n that represents the cooldown period between two same tasks. So for example, if you want to execute task A, there should be at least n units of time before executing same task A. And we have to return the least number of units of time that the CPU will take to finish all the tasks. Please note, we just have to return the number of units of time. We don't have to return the order in which the CPU executes these tasks. Now let's take a look at an example, try to understand the problem and come up with a solution for it. Here is an example tasks with a cooldown period of 2. The best practice for any problem would be to come up with a brute force approach and try to optimize it. So what would be the brute force approach for this problem? In the problem, we are given that we can execute these tasks in any order. How about we generate all possible orders while maintaining a cooldown period and pick the order that has least unit of times. Here is an order that we can start with. In this order, for each task we added a cooldown period. This order satisfies the constraint of having a cooldown period, but it's not the best order yet. How about we generate all permutations of this order and pick the order that has least number of units of time? For example, something like this. Why is this the best order? Even though the length of the order is 16, same as the order we started with, but truly we are only using 7 units of time to execute all the tasks, and rest of the tasks after the final A is just idle. So we can actually get rid of all these idle units of time, and we only need 7 units of time instead of 16 units of time we started with. And you can prove to yourself that this is the best order. And the runtime and space-time complexity of this brute force approach is, let L be the length of the input tasks array, and the length of the order we started with is this, where L is the length of the tasks, minus 1 because we don't need to add cooldown period for the last task, multiplied by n plus 1. N is the cooldown period we need to add per task we execute, and plus 1 is 1 unit of time to execute the task itself, and the final one is for the last task. So let's simplify this and call this as x. So to generate all permutations of the order we started with, it takes x factorial amount of time, and for each of those permutation we need to get rid of the final empty slots which are idle, and it takes about O of x time for that. So the final runtime complexity is this, and the space complexity is O of x, because we need x units to store the order. Next, how can we optimize the brute force approach? Let's start with the final solution we have here and try to look at any patterns we can identify. This is the final solution we found using brute force approach. Let's try to notice any patterns here. In this order, we started with the most frequent task, A, and between the same task A, we added other tasks, same here and same here. So that acts as a cooldown period for task A. So can we calculate how many units of time is needed to do something like this, where we execute just the most frequent task and add cooldown period between them and slip in other tasks in those cooldown periods? So this is the number of units of time that CPU takes to execute the most frequent task. Let's call the most frequent task as M, where M is 3 in this example, and this is the number of units of time needed. So how did we come up with this? M minus 1, because we don't need to add cooldown period for the last task. So that's why M minus 1, and N multiplied by N plus 1. N is the length of the cooldown period, and plus 1 is the unit of time needed to execute the task itself, and plus 1 is for the last task. So this is the amount of time needed. So let's plug in M equal to 3 in this formula. So it's 3 minus 1, N is 2, 2 plus 1 plus 1 is equal to 7, which is the same number we got using the brute force approach. So will this formula work in all cases? In this new tasks array, I just added task B to the previous example. So as you can notice, task B also appears 3 times. Is this formula still good? Let's plug in the numbers. M is still 3, so it's 3 minus 1, N is 2, 2 plus 1 plus 1 is still 7. Is there a way to execute all these 7 tasks in 7 units of time? Let's try to come up with the order ourselves by maintaining a cooldown period between those tasks. So the best order while maintaining the cooldown period and execute all these 7 tasks is this. This is the best order in which we can execute all the 7 tasks while maintaining the cooldown period. As you can notice, we need at least 8 units of time. This order is pretty much same as the order before, except we added B at the end, because we could not plug in B in any other task, otherwise it would violate the cooldown period constraint. So what went wrong with our formula? What can we change in our formula to accommodate this case? The last plus 1 in our formula is for the last task that we have to execute, and it's also the most frequent task. In this case, there are two most frequent tasks. So we could change this number to 2 because at the end we will have two tasks A and B that have the same frequency left over. So let's call the number of tasks with the same max frequency as y. So instead of 1 in the formula, we can replace it with y. Here is the same formula. As you can notice, I've replaced the final term by y. Will this formula work for all cases? What about the cases where y is the number of tasks with the most frequency is greater than n? Y is greater than n. Let's take another example and check if the formula works. Let me clean up some space here. Let's look at this new example where we have 14 tasks and the frequency of each task is in this table where A, B, C, D, all of them appear 3 times and task E appears 2 times. So the maximum frequency of any task is 3 and number of tasks with that maximum frequency is 4. So y is 4. Clearly in this case y is greater than n. N is the cooldown period. So let's plug in these numbers into the formula and see what is the result. So m is 3, so 3 minus 1 into n is 2, 2 plus 1 plus y is 4. So this amounts to 2 into 3 plus 4, which is 10. This clearly, the amount of time we calculated using this formula is clearly less than the number of tasks we have. The goal is to execute all the tasks in the least number of units of time possible. So the units of time has to be greater than or equal to the number of tasks we have. So whenever we have more than n amount of tasks that have the maximum frequency, this formula doesn't work. So why doesn't it work? This formula assumes that we are adding a cooldown period of n always. So when we have more than n most frequent tasks, we can obviously execute more than n tasks. Basically, we can make the cooldown period to be more than n. The problem just asks us to maintain a cooldown period of at least n. We can increase the cooldown period. In this new larger cooldown period, we can execute the other most frequent tasks. For example, the order in which we can execute these tasks is in this order. We are keeping a gap of more than n between two same tasks. The same goes here as well. So the gap between A is greater than n. So this is the best order we can execute these tasks in with the least units of time. And as you can tell, the length of the order or the number of units of time needed to execute this order is 14. So whenever we have more than n most frequent tasks, this formula doesn't work, and we can easily return the length of the task itself, because we can find an order that will execute all the tasks in those many units of time. So the final formula is this, where we are taking the max of either the number of tasks that are given to us or the same previous formula we had before. So this formula handles the case when the number of most frequent tasks are more than n. So this is our final formula. Let's write the code for this. I have already copied the formula that we derived before, where L is the number of tasks that are given to us, M is the maximum frequency of the tasks, and N is the cooldown period, and Y is the number of tasks with maximum frequency. So all we have to do is find each and every item of this formula and then just return the result of the formula. So L is length of tasks that are given to us, and M is the maximum frequency of the task. So let's find out the frequency of the task using the counter, which takes tasks as input, and we want to find the maximum frequency. So if we look at all the values of this dictionary, we'll be able to get all the frequencies. So let's convert it into a list. So these are the list of values, and if we take the max of this, that will be the M. Max of values is the maximum frequency, and we need to count the number of tasks that have this maximum frequency, which is Y is equal to, we need to count number of tasks with this maximum frequency. So then we finally just return the value of this formula. So let's try to run the code. It passes the test, submit it. As you can tell, it's the most optimized solution. So the runtime for this solution is to calculate all the frequency of each and every of all the tasks. We just need to go through the whole tasks array. So the runtime would be big O of L, because we are going through the whole list of all the tasks. Even to find the max and the frequency, everything, it takes O of L amount of runtime, and again space is also same, O of L, because we are saving all these tasks in a dictionary. If you found this video to be useful, please like the video for the YouTube algorithm and subscribe to the channel. I will see you in the next video. Thank you.